Hey everyone, in this video we're going to walk through the R code to actually let you do the likelihood ratio test that we've been talking about all this time. And I wanted to start by showing you where you can find the latest guide to these tests. I actually put together a guide in R Markdown and I keep it updated over on my homepage. So if you go to my homepage, it's Google me and NC State, and you'll get a link to me, and then you'll see a menu says our resources. Click that, and it's the first one. This one was last updated March of last year, and the reason we updates is occasionally the MERT package changes a couple things in how it processes the output, and so my functions will occasionally break or something like that, but I'll keep it up to date here if you ever need it, and this is the place you can go to find it. It's also on Moodle, of course, but this will be always be the the latest version after this course is over. And this is in R Markdown, so you can get the code out of there. I also put together a version just in base R because I think that's easier to show you as we walk through it. And in this first video, like I said, we're gonna take a look at how to do this stuff. And to do this, we're actually going to use simulated data. This is the data that's actually in the MERT manual for how to use some of the functions here. So I wanted to keep it consistent with what MERT has in the manual. And so to do that, instead of using kind of real data, we're going to simulate data. And the nice thing about simulated data is we know the parameters. Right? We actually know the population values that the parameters are estimating. So we know for a fact with simulated data that we have diff, whereas if you just use a sample data, you don't really know if diff's in there or not. I mean, you can run the analyses and it'll tell you if there's diff, but you don't really know if it's correct or not. And that's sort of the whole point of simulation studies. If you haven't really, spent a lot of time with them, simulation studies are all about setting up conditions that you know are true, and they're useful for things like evaluating statistical tests. Do the test actually tell you what and result in the right answer? So I've used them a few times in my own work, just kind of evaluating things like likelihood ratio tests in both CFA and IRT. So that's what we're going to look at today. We're going to start by looking at the data itself. So the first time through, we're really going to kind of break into one of these functions here so you can understand the nature of the data that we are simulating. Okay, so what we're going to do, we're going to go through the function and the simulation function, and then we're going to backtrack and kind of run all this together so you can actually see how to do the test. So the data we're going to use in this data set is created with this make data function right here. And we could just run this and trust that it gives you, kind of what I tell you it gives you, but I really want you to understand a couple things. One is like exactly what it's doing in case you need to simulate your own data. And there are kind of packages out there that'll simulate IRT data for you. But in case you need to know how to do it kind of from scratch, this will do it for you. And then also I want to show you how to actually know what's going on in a function. So, the whole point of a function is you make this kind of convenient wrapper, as it's called. And you can see what it means. It's literally wrapping the code. And the idea is that you can, change an input called a parameter into the function. And in this case, this function takes one parameter, just n, sample size you want, and it will return back something, from you. So hallmarks of the functions in R is really different. Just about every other function and is defined in every other software, programming language. Function always comes like first, but in R it doesn't for whatever reason. And so the way to read this code is the name of the function is make.data. And the function then is defined using that kind of, the operator to define it as a function with one parameter n. So anytime you call this function, you'll need to give it n, right? You'll need to tell it what sample size you want. And then from there, the function goes and does a bunch of stuff. So how do we actually know what the function's doing? Well, the best way to do it is to walk through it line by line manually. So we know it takes a parameter n, so we need to specify n, and then we can walk through this line by line, just like it was normal R code. We don't need to actually, look at it as a function. We can look at it just as a bunch of R code. The advantage of using a function, again, is it's convenient. And so all these variables, when you run it, just, and call make data with an n of 1000, like you see down here, is that it doesn't keep any of these temporary objects, A and D1, D2. All this stuff is temporary when it's inside a function. So it doesn't end up over here in your global environment where you have to remove it later. So that's one of the nice things about a function. And when you're using all these different packages we're using, like MERT and whatnot, these things are all just functions. This MERT command is just a function that Phil Chalmers has written. Item fit is just a function. So all these things we've been dealing with all semester, they're really just functions, coefficients of function. And you can write your own function if you are so inclined, and this is what they look like, how to do it. So let's take a look at this and understand what this function is doing. And in order to kind of go through this function line by line, we need to first specify the parameter of this function n. And we're just going to run this line of code right down here. I'm going to just click right here, and I usually use the keyboard, but so you can see what I'm doing, I think I'm just going to click on run. And so we ran this one line of code. We've set n equal to 1000. You can see that over here. So now that we've got n defined, we can just walk through this line by line. So I'm going to first run this first line of code, and it's a weird one. It's called set seed. This is sort of a little bit of an inside baseball kind of thing. Set seed, so computers can't really generate random numbers that are truly random. They need something called seed numbers. And then it does a bunch of mathematical operations that gives you something that looks random, but it's not really random. Um, if you don't specify a seed number, what happens is your computer or the software will almost always use something like the computer clock down to like the the millisecond or whatever from some year. I think it's like 1970 or something. And it uses that as a seed, and what you get then is a different set of data every time. Well, for something like an illustrated purpose, it's helpful to always get the same data out of this. We don't want new random data every time. We want to have data that are repeatable. And so we're going to specify this seed value manually just by running that line of code there. And that's going to set the seed. Instead of being the computer clock, it's going to be 1, 2, 3, 4, 5. It's always going to be the same. So anytime we run this line of code calling the rnorm function, which is this random, basically asking for a random variable, it's always going to give us the same random variables. So that's what that line is all about. Next thing we're going to do is we're going to make a matrix of A parameters. So I'm going to run this. This is going to be A parameters for our group. If I double click it here and look at it, you can see it's just a vector for 15 items. It's 15 items A parameters here, and that's what we got with that line right there. It's giving to us a matrix format. It's essentially just a vertical vector. And what we're asking for is, you always read these functions from the inside out, is to let's run it this way. To first compute random variables. And rnorm means a random variable with a normal distribution with a set mean and variance. And you can kind of see if you type randnorm down here, right? You can see what it's doing there. So it's it's giving you a bunch of stuff, and you can see what those parameters are. It's usually the the how many you want, 15, what the mean is, and the mean here is 1, and then what the standard deviation is 0.3. And you could manually specify that as you want, but we've asked for 15 random numbers with a mean of 1 and a standard deviation of 3 in the population. The mean of these 15 won't be exactly 1. That's the mean in the population. So if we had like a million of them, the mean of them would be 1. But here it's just going to be some sampling error in there. And you can see they vary around 1, and they don't vary a whole lot. That's because we gave it these parameters here of mean of 1, standard deviation of 3. And then we're saying take the absolute value of that, just in the odd chance that something comes up negative, make it positive. I don't think we actually need that with this, but that's what it's doing. And then put it in matrix format with one column. So take these things from this vector format and put them into this format where they are in a matrix with one column. That's what's happening there. Next thing we're doing, we're going to compute these D parameters. These are not the B parameters. Remember the D parameters, that different parameterization where it's like D is equal to like negative, I think, B over A, I want to say. And we saw that earlier on. This is sort of what MERT uses internally, so we're going to go with that. We can compute B from these, but that's what we're doing. So these are going to be the base D parameters, which are kind of like your B parameters, but they're kind of reverse ordered. And this is what they look like. You can see again, we're asking for a group of random normal with a 15 of them, so it comes with 15 items with a mean of 0 and a standard deviation of 0.7 here, also in column format. And then we need, for polynomous data, we need multiple D parameters. So we're going to make this line of code is kind of nests a few different things in here. We're going to take these and we're going to make them for both group 1 and group 2 by C binding D, and then we're going to get the next D parameter by taking D minus 1 and D minus 2. So if you do this part first, you can see what you get. It takes D, and then it takes D minus 1 and then D minus 2. That's what we result in here. And Then we're going to make that equal to both D1 and D2. So we're going to create two new variables here, D1 and D2, and set it equal to that. So right now, this is going to be the D parameters, which are like the B parameters a little bit for group 1, and this is going to be for group 2 right here. You can see there's, they're the same right now because we just set them equal to that formula. So big picture, we've just created essentially like D parameters, which are like B parameters for two groups. Right now they're equal. And this is where we're going to introduce the diff. We're going to say for the group 2, right, in the D2 parameters, and for rows 13 through 15, so items 13, 14, and 15, we're going to take the D1 group parameters and we're going to add a 1 to it. And that's where our diff is. The D parameters for items 13, 14, and 15 are going to be different by 1 for group 2 from group 1. They're going to be 1 higher in group 2 than group 1. So if we run that, what we see now is the D1 and the D2 are no longer identical. So the D1 and D2 are identical up through item 13. And then when you get over to item 13, you can see that they are 1 higher so look at like for group 2. So D1, item 15, the first D parameter is 0.598. And for group 2, it's 1.598. So you can see that's where our diff is coming from. We have introduced diff by taking the group 1 item parameters and changing it to get group 2 item parameters. So now that we have our item parameters for group 1 and group 2, we're actually going to simulate data. We're going to use the sim data function. So the first thing we're going to do is we're going to specify the item types we want. We want graded, and we're going to repeat that. So if you just like look at item type, you can see it gives us 15, a vector with 15 of the word graded typed in a row. So basically, we're going to use that in the sim data function to say we want a graded response, and then we just told it how many times to repeat that was the number of rows in A, which is 15. And so item type is just the word graded typed 15 times in a row. And now we're going to simulate two data sets, one for group 1 and one for group 2. And we're going to use the sim data function. You can do the help function to see what that is. And we're going to ask for the A parameters we specified, which are the same for both groups. And for group 1, we're going to use the D1 parameters. We're going to ask for the N that we specified, 1,000. And then we're going to, item type we want is the graded response model item type. And we're going to do that for group 1, and we're also going to do that for group 2. And for group 2, instead of using the group 1 item parameters, we're going to use the group 2 item parameters, the D2 parameter there. And we're going to then, what we're going to do is we're going to simulate that data for group 1 and group 2. And then we're going to put those together. So RBind just stacks them, right? Group 1's data comes first, and then group 2's data comes. And then we're going to return that out of the function. We're going to run that line since we're stepping through it line by line. So we end up with 2,000 cases at the end, 15 items of simulated data where we know the kind of the correct item parameters for these things are the ones we looked at up here with the D1 and the D2. And that's what that function does. So I'm going to end this first little segment by just going through this function and walking through it. Now that we have this all in a function wrapper, we can just I'm going to go back and kind of delete everything. So clear all that out. We're going to load some libraries we need here. And I'm going to run down here and load this function. So I'm just going to execute this code. It's going to read in that entire function. I've defined it. So it's just like if it were specified in a package or something. And we're going to, again, specify the sample size we want, and then we're just going to call that function. And that function, when we call it here, make data, telling it how many we want, it's going to just create this data set for us and call it dat. And you can see when we run this whole function, none of this junk over here, these objects we made are in our environment because they were all just temporary for use by that function, which is really nice.